All right, welcome back. We're going to be looking at Shifrin today, 1.3.7. That's Chapter 1, Section 3, Problem 7. Okay, so this one we have to let v1 through vk be vectors in Rn, and let's take this other vector v, no subscript, just v, as another vector in Rn. What we want to show is that when the span of the v1 through vk vectors is equal to the span of the v1 through vk vectors and v, that's equivalent to saying that v is in the span of v1 through vk. Really, all this is really saying is if by adding a vector to a span, right, you take a list of vectors and you take the span of them. If by adding a new vector to it, you didn't change the span, hence they're equal, that's really just the same as saying then, well, then your new vector must have already been in the old span, right? And likewise, if you take a vector that you know is in the old span and you try to add it to the end, you don't create anything new, right? Geometrically speaking, if you take a plane, there's a whole bunch of vectors in it, say, in R2, and you just take another vector in the plane and throw it in, right? If you take that third vector and throw it in, you don't get anything new, right? If you take all linear combinations, you just get the same plane. You're just adding another vector that was already there, okay? All right, so we're going to go ahead and prove this. All right, so this is an equivalence statement, right? So material equivalence here saying that, this statement here, P, if and only if this statement here, Q. So remember, to do this, you're going to have to show sort of both directions. It's kind of nice when you can come up with a really solid, elegant, statements of equivalence. In other words, if you can show if and only if statements again and again and again, then you don't have to do it the way we're going to do it, but we're going to kind of split things up and keep it simple. In other words, we have to prove this direction, so we need to show that this implies that, and then we also have to prove the other direction. This implies that. We're going to go ahead, just because we're going to start with this statement showing or implying that statement, and then afterwards we'll assume this one to imply that one. So first we're going to move the proof in this direction. So we're going to assume this and show that. So let's do that. So let's have that v belongs to the span, and I didn't capitalize, whatever, v1 through vk. Right, so v belongs to the span of v1 through vk. Now remember, what does it mean to be in the span of v1 through vk? Well, remember, the span of v1 through vk is just a set of all linear combinations of these vectors. So what we know is that v is a linear combination of these vectors v1 through vk. In other words, it's just something times v1 plus something times v2 plus something times v, and all the way up to vk, right? It's just some linear combination. Now, clearly, the span of v1, v1 through vk is a subset of the span of v1 through vk and v. So we assumed this. What we need to now conclude is this statement, that the span of v1 through vk is equal to the span of v1 through vk and v. And remember, these are two sets. I mean, they have additional structure. They're actually subspaces. We've shown that the span is a subspace, but I mean, that's beside the point for the moment. We can think of them as sets. And so what we really need to show is set equality. We need to show that this set equals that set. And if you remember, the way to do that is we want to show that this is a subset of that and that that is a subset of that. One direction here is pretty basic, though. I mean, if we have v1 through vk, no matter what, I mean, in this special case that v is in the span of v1 through vk, it's going to be the case that we don't really add anything to it. But I mean, this is always going to be a subset of that, right? This is fewer vectors. If you really, really want to get that direction, you can try to do the proof. It's going to be pretty straightforward. So we're going to take that as sort of obvious. So we're not going to show that direction, that this is a subset of that, because that's pretty clear, because we have v1 through vk and v1 through vk here. We're just adding an extra v. The question, though, the thing we do definitely have to clarify is that this is a subset of that, because that's not clear. Okay? That's sort of why we need this statement, because in general it's not true. So we need to show that. Okay, so we know that this is a subset of that. I want to show that that is a subset of that. So what I'm going to do is I'm going to take an element of this and show that it has to belong to this set as well. So I would pick V. That would be a nice thing to pick, but I've sort of already picked that one. So I'm going to go ahead and say let U belong to the span of V1 through Vk with that little extra V hanging at the end. So what we know is that U is a linear combination of all of those vectors. So it's some, I'll put beta I Vi plus beta k plus 1 V. So here's what I did. Okay, U, it belongs to the span of V1 through Vk and V. So it's a linear combination of these things. So I mean, technically I could have squashed this all down into the sum, right? I'm using sigma notation, but I'm going to do something. So I intentionally leave out the V. So right now, notice this is V sub I. This thing doesn't have a subscript. So this summation, this sigma notation here is going to take care of this part of the linear combination. And then I'm just going to throw in this extra whatever it needs to be, right? It's a linear combination of all of these, and that's what I've got here. But here's what's going to happen. Watch. OK, so I'm summing these up as a linear combination, and I have this little extra guy out here. But wait a second. V, remember, by assumption, was in the span of V1 through Vk. So I can write V as a linear combination of these guys right here in this way. So here's what I'm going to do. This thing stays the same, right? This I equals 1 to k of beta sub I, V sub I, plus beta sub k plus 1. But now V here, here's what I'm going to do. Instead of writing it as V, I'm going to write it as a linear combination of the V1 through Vk. So that's times the sum from I equals 1 to k of, and this was alpha I, Vi. Right? So here's what I'll do. I'll distribute that beta into the sum. So I'm going to get the sum from I equals 1 to k of beta sub I Vi plus the sum from I equals 1 to k of beta sub k plus 1. Now this one's not changing. It was sort of like a constant with respect to this sum. But now these alpha i's, we're moving the index across the alpha i's and the vi's. Right? But now look, these guys are indexing on the same range here from 1 to k, and with respect to the same vectors, the vi's, v1 through vk. So I'm going to combine that into a single sum, I equals 1 to k. And I mean, I could skip a step, but let's do this step by step. So it's this thing, beta I, vi, plus this thing, beta k plus 1, alpha I, vi, right? And now I can pull that vector. So these are vectors, the vi's, and then the betas and the alphas are going to be coefficients. So I can pull out that vector vi and just leave the betas and the alphas as coefficients. So I'm going to write that as the sum from I equals 1 to k of, OK, there's a beta I here, and the vi, which I'm going to pull out, plus beta k plus 1 times alpha I. And then I pulled out my vi. But look at this. That's a linear combination of the vi's going from 1 to k. So that's a linear combination of these. So when I took an element u here from the span of v1 through vk and v, I got it as really a linear combination of just the v1s through vk's, which is an element of the span of v1 through vk. And so this is a subset of that, and hence they're equal. OK, so that's this direction. We've shown then when v is in the span of this thing, all we really got to do is basically rewrite this v here in terms of the others. And then that linear combination, we can just put together all the coefficients, and it's really like just getting rid of the v, and you end up with the span of v. That's the basic idea. OK, now we've got to prove the other direction. So I'm going to clean up the board here, and we'll work on that. OK, so now we're going to prove that assuming that the spans are the same, we're going to get that that means that this extra v here that we threw into the span is really just an element of the previous set, the span of v1 through vk. So to that end, let's do this. Let the span of v1 through vk equal to the span of v1 through vk, and throw in that extra v. OK, so if that's the case, what we're saying is any linear combination of the v1 through vk and the extra v can be written as a linear combination just of the v1 through the vk, right? And what we want to show then is, well, that's basically what this is saying. So we're kind of, in some sense, saying it sort of makes it obvious. But what we want to do is we want to show it algebraically so that we can see that this is clearly the case, mathematically speaking. So to that end, here's what we're going to say. Let's take an element from the span of v1 through vk with the extra v. So that would look something like this. I equals 1 to k of alpha I vi plus alpha. Oh, OK. No, actually, let me take my mistake. Not just any arbitrary. So that was my mistake. We're not going to take an arbitrary element. We're going to take an element that looks like this. OK? So this part of it is arbitrary. Just take anything you want, alpha i's. So take any coefficients of the v1 through vk, alpha I, alpha 1, v1, alpha 2, v2, so on and so forth. And then just add the v to it. In other words, we're going to take a linear combination from this of the form alpha I vi summing up plus the coefficient of v here is just 1. So it doesn't matter what these coefficients are, but we're going to force that coefficient to be 1, which we know is an element of this, because this is just all linear combinations, in particular this one. And here's what we're going to do. We know that since these are equal, there has to be some linear combination of just the v1 through vk's that is equal to this element, because if I picked an element from here, it should also be in there, but the elements in here are of the form, and I'll put beta I vi, I equals 1 to k. So these coefficients, they're different. They very well, they're going to be different. The beta i's and the alpha i's are not the same, but in the end, since these two sets we're assuming are equal, every element of this set is of this form, and I picked a specific element from this set, and it is of this form. Doesn't matter that I picked a special one here. There's got to be an element here, a representation in v1 through vk that is equal to it. OK? So now that I've written the element from here in terms of a linear combination of the v1 through vk's, all I've got to do then is show that that means that v is in the span of the v1 through vk's. What does that mean? It means that v is the linear combination of just the v1 through vk vectors. Well, if I move this sum over to the other side, I'm going to get v equals this guy minus this guy over here. But now we just play the same trick that we did before. Just kind of move everything together, and you're going to end up with this. And what I have then is that v is a linear combination of the v1 through the vk vectors, which means if I can write v as any, it doesn't matter, if it's a linear combination of these vectors in any way, if I write it in any way, then it's in this set span of v1 through vk. Which establishes what we wanted to show. We wanted to show that when we assume that these two sets are equal, then that must mean that that little extra guy that you threw on there was really just an element of the original set span of v1 through vk. right? Because I can write it as a linear combination of the vectors v1 through vk. Okay, so there was nothing too tricky here. This was just, in some sense, it's sort of writing out. It's a good exercise for trying to sort of iron out details that are sort of intuitive, right? Adding a vector to this thing, if that vector was sort of already in this set, then you didn't really do anything. That's really all this is saying, is if I take something, pull it out, and throw it back in, I mean, it doesn't really do anything. I get the same set. All right, and these are just sort of different ways of saying that. OK, I hope this was helpful. And that's the proof. I'll see you on the next solution.